Hello everyone. This is lecture 1 part 2. In part 1 we talk about the definition of power electronics, and also we talk about the switches, static switches, and converters, which is AC to AC, AC to DC, DC to DC, and DC to AC. Now, as I told you, we will start with AC into DC, which is a rectifier, and we're going to spend a lot of time, which is from now till the midterm. And this is the first topic, which is single phase half-wave uncontrolled rectifier. So we're going to spend in single phase maybe 3 lectures. So single phase half-wave, and then next time we will take single phase full wave. And after that, we're gonna take, this is all under rectification, under AC into DC. And then after that, we're gonna take 3-phase. We're gonna take 3-phase half-wave rectifier, and then 3-phase half-wave full-wave rectifier. That's uncontrolled. Still under rectification, we will jump to control, which is using the thyristor, and we will repeat the same thing. We will repeat this by replacing this power diode by a thyristor. And we will repeat everything. It will be single phase half-wave controlled rectifier. It will be single phase full wave controlled rectifier. It will be 3-phase half-wave control. It will be 3-phase full wave control. And then the midterm one comes. Anyway, this is the first topic of AC into DC. It will be single phase half-wave controlled rectifier. We have a circuit. We have a source right here, and we have the power diode right here. We know that the power diode is one-way path. So the current comes from the anode to the cathode. It cannot come the opposite. It cannot go through the opposite, which is from cathode to anode. So the current will come here through the power diode, and it will come to the resistor, and it will come back to the neutral. This is line and neutral, okay? This is, let's say, 4N in lab. You're gonna choose 4N in your lab. Yeah, this topic right here can help you in your experiment number 1. So watch this before you come to lab. Before you come to the first lab, which is you can look at in your manual, which is the first topic, which is this topic. So watch this, and then you can come ready to the experiment. Just do the connection. Okay, let's see what will happen here. This is the V source, which is AC, positive, negative, positive. I'm gonna draw 1.5 cycles, because I want to draw this part right here for the resistive load. And then we will add inductive. That's what you will do in your lab. You will do the whole thing with resistive load, and then you will add the inductive in series with the resistive, and you will have different waves. So I'm going to draw the resistive waves right here, the output with the resistive loads, and I'm going to draw the output with the inductive loads right there. Let's see right here what will happen. It's half-wave, means that I will see only the positive. So that's what I will see. That's the way if you want to draw it neat and nice, you count 1, 2, 3, put the peak, start from the peak point, and then from your peak you go back to 0, and then you go to 180, 1, 2, 3. 1, 2, 3. So you start all the time from your peak if you want good drawing and nice drawing. Then we know that from here up to this point it will be 0. From here, from 180, we know that this point here is 0, and we call it alpha. This point here, we call it alpha, and it's 0. And this point here, we call it beta, and it's 180 in our case. And here, that's 360 right here. Okay, that's 360. And it's all 0 up to here, because the positive will go through, this positive will go through the power diode, the negative, this is positive and this is negative. The negative try to go, but it cannot go through. The negative cannot go through. And then Same thing here. As I told you, count 3, 1, 2, 3, start. This is the peak. Then you draw, you go back here to your point, and you go draw here. And that's my output. That's what you will see in your oscilloscope, and that's what you must get. The current will be the same. The current will follow the voltage, but the peak is less. It's approximately half. So the current, all the time current follows the voltage. So you just put the current here if you want to draw it. Same peak, but half. And then you draw the same. That's here. Current is 0 right here. And then you do the same here. Okay? This is the peak. And then you go to your point. Okay? So this is I max. This point. And this point is V max. And this is V out. And this is I out DC. It's now DC, guys. It was AC before. This one V source AC. Okay? But the output now is DC because the polarity is only positive. So now the output is DC. Okay? So we said that this point is beta and this point is alpha, and from this point to this point right here, from this point to this point right here, we call it gamma, from here to here. Okay? So if you want to find gamma, gamma equals beta minus alpha. In our case, in uncontrolled, all the time alpha will be 0. It will start from 0. We're not controlling the firing angle. So the alpha will be 0. And if it's 0, then, the alpha will be 0. So the gamma now, in this case, if this is 0, gamma equals beta all the time in uncontrolled rectifier. When it's controlled, it's a different case because we can start in any point. We can start at any point. Okay. V diode, which is the voltage across the diode. The voltage across the diode. I want you to pay attention to this. This device here works as short circuit, as we stated before in the introduction. It works as a short circuit or open circuit. If it's a short circuit, it's like a wire, means there is current. And if there's current in a wire, the potential difference between voltage is 0, so no voltage. But if it's open circuit, means there's a voltage. Okay, if you look at any plug, this plug right here, you cannot see it, in any plug. You measure the voltage, there's a voltage. But if you connect a wire, if you close the circuit, if you try to get the voltage in actually the same point, no potential difference, no voltage. So when this is a short circuit, when it's conducting, if you try to measure the voltage, it's 0. Okay? So when it's conducting here, it's conducting during this time. See here, that's the current, the red, it's conducting. So I know that during this time, since it's conducting, my voltage is 0. Okay? Same thing here. It's conducting, so I know that my voltage is 0 up to this point. So what's the voltage? What's the voltage of the V diode? What's left? What's left here? Okay? So you start from your peak. What's left from the source? Negative? Yeah, it will be negative. So here, I start from the peak. Start from the peak here. Okay? Wow, that's V diode. That's what you will see when you just add resistive load by itself with no inductive. We know that the resistive load represents lights and anything, and the inductive loads mainly represent motors. Okay? And it's not that when we draw, because we will have an issue, we will have a small issue when we connect inductive, we will come to it. Okay? Okay, let's say what, in this case, what will be the I source? This is a very good question, guys. What will be the I source in this case? I source. I source, since this one is open and closed, when it's open, there will be current. When it's closed, there will be, when this is closed, there will be current. And when it's open circuit, no current. Same for the source and the connection. The circuit is in series. So I source, same as I out. Okay, this is I source, and then 0 here. Okay, and then same thing here. Okay, this is I source. I source, same as I out. Okay, that's for resistive load. If we come here and we add a load, which is inductive load. Let's say it's a motor. We will see what will happen now. And here you need to pay attention a little more. Okay, that's the V source, same as there. And now I want to draw the V out. So this is here V out DC slash I out DC. Let's see what will happen here. The V out, let's see here. Now we will have this here, which is resistive and inductive, connected in series, and we will put it here. The current will go there, the current will flow through the diode, and it will come through the resistive and then the inductive. And we know that the inductive stores current. Inductive stores current, capacitive stores voltage. So this one here will store. The more current that flows through, it will store current more and more till it's saturated, till it becomes saturated. Then during the negative, nothing is going there. So what will happen? This inductive has to release what it has. So what will happen? The polarity will flip. Before the polarity was like this. Now, when it flips, the polarity will be like this, and it will work. This inductive will work as a source. It will release what it has till it's done. Okay? Put this in mind. You can repeat the video if you did not get this. Okay, let's see what will happen here. It will happen first the same. 1, 2, 3, the peak. So you start from the peak. Okay, and then 1, 2, 3 here. So here. Okay, same thing here. 1, 2, 3. That's my peak. 1, 2, 3, and that's my 0. But what will happen here? Is it the same? No, it's not the same. Since we have inductive, as I told you, inductive will work as a source. First, let me repeat this. When the current goes through, during the positive, this will store current. Okay, will store magnetic field, current. And then, during the negative, nothing is going there. So what will happen? The inductive will work as a source, so the polarity, it will start releasing. When the current starts decreasing, polarity flips, and it will release. So the current now will go back through the circuit till it's done, till it releases everything. So I will draw the whole thing, and you guys will see. If I draw it like this, I'm gonna draw it with dots. Okay, see here. 1, 2, 3, that's a peak. Okay. Okay. So let's say this is what we will see, same as before. But now the inductive, we said it will release, so we will have a ripple right here. The inductive depends how much it stores. Let's say it stores small, so it will stop right here. If it stores more, it will stop right here. Okay. If it stores more, it will stop right here, and so on. So let's assume that it stops here. So this one here is 0. And same thing here. Something like this. Okay? So that's, now my wave is different with inductive load. Okay, let's see the current. The current will look different than that. It will start from 0, yes, but the peak will not be here. The peak will shift. Okay, the peak will shift, and it will start when the voltage stops. The current will start when the voltage stops. So it will go, the peak, as we said, the peak will shift, and it will go like this. Now this one here is I out DC. And now, yes, this one here is alpha equals to 0. And now this point here is beta. And it's greater than the 180. It's maybe here, if you look at it, it's 240. Now beta is 240. If it's here, it will be 270. Okay? So before here, gamma equals 180 minus 0, so equals 180. But here, it will be gamma equals beta minus alpha, so gamma equals 240 minus 0 equals 240. Okay? 240. And the current is longer right here. And then it's 0 right here. And it's the same here. And so on. Okay? What will happen for the V diode? This is V diode right here. The voltage across the diode. As I told you before, the voltage across the diode, when there is current, when it conducts, it's 0. So here, we have a conduction from here to here. So that's conduction here, up to here. So this is all 0. Up to this point, 0. And it conducts here, all 0. When it's red, it's conducting. It's not conducting here. So what should I do? I draw the whole wave, which is here. Okay, I draw the whole thing. Okay. Then this is here. And then I go from here. This one here should be 0. And this is my V diode. Okay. See here? Since it conducts here, it's 0, and that's what's left. This is what's left. This is V diode. This is with inductive load. And this is with resistive load. Is this okay? Is this good? Or why we add inductive? I mean, we don't like this ripple, by the way. Let me tell you this. Issues here, issues. Voltage will go down. Current will go down. Means power is going down. And we don't like this. We don't like this. So what should we do? What should we do to fix this issue? Because now, I mean, why we add inductive, as I said before, we're not adding inductive just to add inductive. No. We are looking for real life application. I mean, inductive represents a motor. You need motor. You need to connect a motor to your circuit. You need to connect a generator to your circuit. And the coils, all motors have coils. So if you connect a motor, you need to do some work, but you have to pay the dues. The voltage and current will go down, the power will go down. Can we fix this problem? Yes, we can fix this problem, and we can fix it with something called freewheeling. So if I come here, if I put this here, as I told you before, I will put this inductive, okay? Now I put this here. This is RL, and that's the V out. We will have that issue. So what should we do? We will add a freewheeling diode. Freewheeling diode. Freewheeling diode. What will happen when we add freewheeling diode, guys? Let's see. Let's let's see what will happen right here. And I want you to pay attention to this point. The current will come here. It cannot go here because this is anode, this is cathode. The current cannot go through the cathode to the anode, so it will come here. What will happen here? It will charge. The inductive will charge. Okay? So the positive will flow through the power diode. The inductive will charge. And then during the negative, this has to release. It has to discharge. Before, it used to discharge through the power supply, through the power diode, and that's now, there's a resistance here. But since we put the freewheeling diode here, we make a short circuit. So it will not flow through there. So the current now, that's the previous current, but now, during the negative process, when this one wants to release, we said the polarity will flip. So the polarity will go like this. And now the current that was stored as a magnetic field in the inductive, it will release through the freewheeling diode. Then it will come back again to the inductive. It will charge, but now the amount is less. It will come again through the freewheeling diode, so it will keep looping, it will keep rotating, okay, till it's finished. But the process will take a long time. So what will happen here, if I come and draw, actually, I will erase this, because I want to draw the freewheeling. Also, you will have this in lab. You will do this in lab. This is freewheeling, guys. This is freewheeling diode. So what will happen? The good thing you will notice in your oscilloscope, in your wave, that the freewheeling will get rid of this. Will get rid of the ripple. Okay. So the freewheeling. The good thing about this freewheeling here. Okay, get rid of ripple. Okay, get rid. Okay, negative ripple will be removed. Negative ripple will be gone. Okay, that's one thing. Two, current will be continuous. Three, improves power, which is voltage and current. Voltage increase and current increase. Okay. Also protect main diode, which is this. It protects this one here because when they build this, the main diode right here, they build it to work for a certain amount of numbers, 4 billion, 6 billion, whatever, 5 million times on and off. So if the current goes here, it will be on once, and when this one releases, it will be on again. So it will work double time. So we make the aging life of the power diode longer. Okay? So what will happen here? Now we will get rid of this negative ripple right here. So this is my peak again. Okay, and 3 right here. Okay, 1, 2, 3, and this is here 3. Okay, get rid of the negative ripple and use just the black because I don't want you just to say same color right here. Okay, and same thing right here. So this is okay, and then the current, guys, the current will go this notice the peak will be right here. It will start right here, this is the peak, and then it will start decreasing, 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 till it reaches 2 pi, guys. 360 degrees, okay? 360 degrees. See here, the current is continuous because of this freewheeling diode. When this one release, the current will go through the freewheeling diode and it will come back and it will charge again. It will charge again. So that's it becomes a loop. Okay? And same thing here. And so on. So that's, let me just show you here in your lab manual. Okay, this is the circuit. I think we have done it before for you guys, but you're gonna redo this, which is the same right here. Okay, and I already explained for you the isolators. So, and then here in this table right here on page 5, you just take the readings. You will notice that the resistive load voltage is higher, and then the inductive voltage is lower. Also the current. See here it was 49, then it goes down with inductive to 38. Current was 0.8, it goes to 0.6, and so on. Okay? The conduction angle is 180, but for the inductive it should be bigger. You should do the calculation, okay? And your drawing will be here, same as those. And then this is the freewheeling. This is the freewheeling. So you're gonna add the freewheeling. And you will notice the change and you will take the reading. Okay, that will be your experiment. And this is your single phase half-wave uncontrolled with both loads. I want you to look for this in chapter 3, guys. So this one here is chapter 3. So chapter 3, okay. Page 65, your textbook, huh? Chapter 3, your textbook. Page 65, pages 65, okay. Page 65. To 68. Also look at examples. It's very important to look at this example, guys, which is example 3.1, page 67. Okay. Make sure you know those equations. I'm gonna write the equations for you next time. Okay, and also the freewheeling diode. For the freewheeling, okay, for the freewheeling diode, look at page 81 to 84. 81 into 84. 81 and 84, okay? 81 to 84. Another thing I want you to look in your notes. If you want the same information in your notes, page 8. Page 8 into page 16. Okay? In your notes, page 8 into page 16. You will find everything right here. In your notes, this is a very good note right here. See here. This is that circuit. Okay, and more information. I advise you really to look at this. Okay, and this is the drawing right here. That's the V source, and this is the V out and I out with resistive load. Okay, and those equations. Okay, make sure you understand those equations. And if you have any question, you can ask me. This is the V out DC. You will find it also in your textbook, but this is a good chart for equations, and the equations will be repeated and there will be one different thing. So this one here, those equations are for both resistive and inductive, half wave, resistive and inductive. There will be one thing will change. You see here, this is V out equals V max over pi, that's for resistive load. And for the inductive, it will be in page 12. It will be V out DC equals V max over 2 pi, 1 minus cosine beta. This is when we have inductive load, okay? So this is the only thing that will change in equation. And those are the drawing in page 13 for the inductive. That's the V source, and that's the I out, V out and I out, and that's the V diode. And in page 14, that's the freewheeling diode, which is we just had here with the green. And those are the advantages of the freewheeling diode. And that's it. This is if you want to add notes here. And this is the drawings for the freewheeling diode, which is at the end right there. Okay, that's it. And that's the second topic. So this will be actually, this is a summary for page 8 to page 16 in your notes. Please look at it and look at this lecture before you start your experiment next week, and it will help you. And that's it. And thank you. And we're done with lecture number 1. And next week we'll do lecture number 2. And I will upload everything for you on YouTube, and I will give you a link in Blackboard. Okay, thank you.